I am a neuroscientist by training, so I was looking at how the brain develops and how early life events impact the developmental trajectory of the brain in ways that enhance risk and ways that protect from risk of developing conditions like depression and anxiety and post-traumatic stress disorder later in life. I've shifted gears a little bit since then, and I work more at the macroscopic level now rather than microscopic with the WHO Collaborating Center for Global Mental Health at Columbia, where our essential goal is to take basic science research, clinical research, and what we know at the population level and implement it. So for today, I'm going to focus on resilience as it applies to individuals, but with the idea that individuals comprise communities and society as a whole. There's something a little wonky about the slides, but that's okay. So the key questions to just frame my brief discussion of a topic that is an entire doctoral thesis and really a field. So you're going to get a circumscribed version of this material. So here are the 4 framing questions. So what are the biological mechanisms underlying resilience? How does early life shape resilience? What role do family and community play? Where does the built environment become a determinant of health? So the last 2 questions really seem kind of very population level and the level of public health and seem far removed from biology. And I'll help potentially bridge that gap for you in a rudimentary way, at least for now. So when I think about resilience, just generally in the way that we've seen it defined and discussed in various conversations that have come before, as well as when applied to an individual, these 3 words emerge for me. So reactivity, the ability to respond, adaptation, and growth. So this idea of not just bouncing back, but bouncing forward. And this is in response to stressors, adversity, and trauma. So my question really is, well, how are these processes, reactivity, adaptation, growth, mediated biologically? So there are many biological systems at play in response to a stressor. So you have the HPA axis that many of you might be familiar with. So that's the hypothalamic, pituitary, adrenal axis. So it's your brain communicating with your adrenal glands that release hormones. The immune system plays a really important role. The cardiovascular system plays a really important role, and the communication within all of those systems. But for today's purposes, and given my background, I'm going to focus specifically on the brain as a mediator of the stress response. Again, in the brain, there are many circuits. So when I talk about circuits in the brain, it really is like an electric circuit because the brain neurons, which are the brain cells that comprise the different parts of the brain, communicate for the most part electrically through electrical changes, right? And so there are many types of brain regions communicating with each other, so many types of circuits that underlie the stress response, the human stress response. And these other circuits that I'm not going to discuss involve things like reward pathways, so your response to reward, self-regulation, executive function, your ability to make decisions, to switch decisions based on new data, for example. The one path that I am going to talk about is the one that seems most intuitive. It's the circuitry around fear responses and stress responses. Okay, so really basically, this is the human brain. This would be where your forehead is, and this is where your neck is. So there are a few, there are obviously many parts, but I'm going to talk about a few structures, some which may be familiar to you and some which may not be. So let's start with the input of sensory information. So that happens here in the sensory cortex. So that's where you see, someone coming at you, or if you're out in the Serengeti, there's a lion running towards your safari vehicle. That's where all that input comes in. Sensory input goes to this structure called the thalamus. It's literally like the organizing center for sensory information, where it collects the information. If it doesn't meet a specific threshold, everybody okay with it? If it doesn't meet a specific threshold, it may not be recommunicated to other places. So when there is an stressor or an input that's strong enough or frequent enough, you do get the sensory input go to the thalamus, which then, in the case of fear circuitry, if it's a stressor that's related to fear or threat or danger, goes to these 4 structures. So 2 of them I'll start with, which will be very familiar to you, the hippocampus and the amygdala, right? Everybody's probably heard of those in some context. So those 2 organs in the brain are really part of what's called the limbic system. The limbic system is really important in stress response and the ability to perceive fear, respond appropriately being an important word when we think about resilience, and then when the fear response is done, to be able to go back to homeostasis, to equilibrium, where it was before, which, as you can imagine, is resilience at the brain circuit level. Another really important structure is the prefrontal cortex. So it's up here near our forehead. It really serves to regulate these lower structures that are really responsive to fearful stimuli. That's where emotional memories lie. That's where traumatic events or events that have specific positive or negative valence or some sort of salience that reminds you of the traumatic event, that's where they lie. This structure up here serves as a brake to that circuit. It says, okay, you have done enough now to get away from danger, you can stop. In people who are at higher risk for developing depression, anxiety, or post-traumatic stress disorder after a traumatic event, there's dysregulation that's occurring in this circuit. This circuit is also a really good case study for when we think about how genetics play a role in determining whether we are at baseline resilient or non-resilient people. Obviously, we all know that it's a much more complex interrelationship between biology and environment that does that, because biology is not destiny, but it does impact the way we react to our environment, so it's not nothing either. So I think it's really important for, especially if many of you are not basic scientists or scientists of the biological kind, how do we know what we know, right? Before I show you what we're gonna see. So we know what we know from things such as animal studies, right? Animal models of trauma and then studying their behavior, animal models of trauma and then looking at their brains. We also know the genetic component from things like twin studies. So 2 people experience the same stressful condition. One maybe does better, one maybe doesn't, even though they're genetically identical. Why is that? Well, that can tell us information about maybe non-genetic or epigenetic changes that might happen. I'll get back to that word a bit later. So what we find is in these studies, and so there's also post-mortem studies of people's brains who have gone through trauma. There's veteran studies, there's studies in the military. So we have a large corpus of data that comes from these various type of sources that really tell us a pretty comprehensive story. And what really emerges is that we don't have all the answers, but many of the genes that kind of determine baseline resilience are involved in pathways like the fear circuitry. And what they do is these genes mediate things like the types of receptors that you have in these different parts of the brain, the type of neurotransmitters that are expressed and released in different parts of the brain. So neurotransmitters are things like serotonin and dopamine, which are probably more familiar to you, and then also things like GABA and glutamate, which are just signaling molecules that cells use in the brain to communicate with each other. So a lot of the genes and the genetic polymorphisms or changes that we see in people who might be more resilient or more vulnerable are often in these pathways, the serotonergic system, the dopaminergic system, and what they do is that they can impact the structure, the functioning, and the communication between these regions. And what it really means is when you're impacting this fear circuit is that these fear circuits then regulate behavioral responses. They can regulate heart rate, the extent to which you sweat, your vigilance, but also emotional regulation, right? Sorry. So this is a scary slide, even for scientists, but I'll walk you through it really fast. So when we think about I just mentioned to you the genetic changes that you're born with that impact the regulation of receptors and these signaling molecules that impact the circuit which can then impact your fear responses or behavior, which can then impact how resilient or vulnerable you might be. Well, it's not just your genes that can do that. More and more we know that the environment can really change receptor expression, the signaling expression, the structure of your brain, the functional connectivity of your brain. And here's an example from my world, or my previous world, where you see here 2 neurons, it doesn't matter which, but imagine it's the hippocampus and the amygdala. So they have this connection. So this is the zoom in and the connection. One is talking to the other. What you have here is a social defeat paradigm. So that's not a genetic intervention, that's an environmental intervention. So this animal is in a socially stressful environment where it's with a predator. What happens is there are some mice that are susceptible, in this case it's a mouse model, and there's some mice that are unsusceptible or resistant. All you need to look at is that the firing, which is represented by this plot here, is higher in the susceptible versus the unsusceptible person. In addition, you have the response in the other neuron much more exaggerated than here, right? There's a lot more P's here, much fewer P's here. You also have changes in these little channels, which are real physical potassium channels, which change the excitability of the neurons. So here you have an example of a social paradigm, so an experience of social defeat, having these really profound biological imprints. A human example of this is adverse child events that has come up in many different conversations. Javier Lopez mentioned it from the Red Hook Initiative, for example, and the importance of really addressing and preventing the experience of early trauma in children. So what are early, these ACEs, so to speak, adverse childhood experiences? They really range, but they usually are things such as household challenges, so you can't really see that, but it's the experience of parental neglect. Malnutrition can be considered a childhood adverse event, abuse. And so as we think about some of the questions that I started with in terms of framing this discussion, some of the risk factors for that impact the circuitry of the brain in this negative way are at the level of families and the level of communities, right? And so we'll get back to that. So, but what is the mechanism by which this early childhood event is having such an impact on the brain such that it's leading to this higher risk and vulnerability for depression, anxiety, stress disorders, which in many ways underlie the experience of resilience versus vulnerability. So here you have brain scans from kids who've experienced early childhood events, and many of these regions will be familiar to you. Hippocampus, the amygdala, prefrontal cortex. Those are all fear circuit regions, and in kids who've experienced early adverse events, these regions, which is what these graphs show, are changed as compared to kids who didn't experience them. Why is this happening? Well, one important mechanism is that your brain is continuing to develop into your 20s. So here you have, the infant brain and embryonic brain to the adult brain. So the brain of children isn't just a smaller version of the adult brain. There's many different processes going on. Its responsivity to certain neurotransmitters is different than from an adult. There's this concept called pruning, which is literally like the gardening version of that, where you have initially through experience. So experience, for example, enriched environment. When you have a lot of play, you have access to food, you are in a colorful, joyful, rewarding experience. You have all of these neuronal connections that are made because you're getting stimulation, and neurons that fire together wire together. That's the neuroscience behaving what they say. And so you're building these circuits and these kind of neuronal communities, so to speak, and they stay and they confer resilience later in life. And as you can see, there's so many brain processes that are going on. So there's the birth of the cells, migration, there's axonal and dendritic growth. That's not so important, but basically different parts of the neurons are growing and connecting to each other, and that's happening all through this really important postnatal period. 4, 8, 12, 20, 24, there's still events occurring. So the brain is really what neuroscientists use the word plastic. There's incredible plasticity. And what we find now is that plasticity extends into adult life as well. And so what are the mechanisms by which these early childhood events, these ACEs, and which really just represent environmental changes that are being translated into biological changes. What are some ways in which that can occur? How do you bridge biology to the environment? Again, this is a huge field, but I've picked out kind of the two real interesting pieces in my mind, and the newest, so it's kind of fresh, not really fresh off the presses, but within the last 10 years or so, we've developed this knowledge. So it is interesting. So there's this field that we've probably heard of in the New York Times through all sorts of mechanisms, is epigenetics. All that means is that it's a change in gene expression that doesn't actually change the gene. So it's not a mutation, for example. It's something that's done to the DNA that makes it easier to read. Okay, it's not a mutation, it's not a change to the actual DNA code. And these epigenetic changes have been shown to occur as a consequence of environmental exposure. So, enriched environment, for example, can create an epigenetic profile that causes the reading of DNA, reading of genes that are really helpful in the fear response, that are really helpful in resilience. Another really interesting phenomenon that we didn't think this existed 11 years ago is this concept of neurogenesis. So when I first showed you the map of the brain developing, the first thing I read off was cell birth, right? So neurogenesis, that means neurons being born. We used to think that this all happened in this circumscribed period in utero, in early life. However, we now know that neurogenesis is going on all the time in adulthood in certain parts of the brain. And one part of the brain that might be familiar to you is the hippocampus. So people think that the neurogenesis that's happening in the hippocampus may underlie resilience, may underlie, for example, the antidepressant response of some therapeutics, not just pharmacological, but also psychosocial therapies. And so what you have is that you have the development of these new neurons that really are blank canvases. They can be integrated into circuits in a helpful manner, or they can be integrated into circuits in a non-helpful manner. And so when we think about resilience, this is really an important component, because not only what it really shows is the potential to change things, that things aren't indelible, but that interventions can be done so that your trajectory can be changed. So if you have experienced adverse childhood events, there is precedent now for mechanisms that can potentially change your trajectory so that you are more resilient. It's really, I'm so sad that this picture is beautiful, and you can see it there, Gary, on the, I'll bring it around later. It's a stain of, the cyan is just neurons in the brain, and then the red are the adult-born neurons in the human brain. And it's just really beautiful the way, all the types of multidisciplines that have had to come together for us to be able to visualize these adult-born neurons in the brain, from imaging to stealing genes from other organisms like fireflies to turn on genes in the brain. I mean, I'm a nerd about that. So, but it's just lovely. So, and it was just my one slide proof that neurogenesis does occur. But this is going to be really important for today's conversation, because again, it's bridging the gap between biology and nature. So it's really hard to see. I'm sorry, again, it's easier there. But what we have here is initial exposure to high stress environment versus initial exposure to high reward environment. Okay, so this is a modifiable thing. And when we're talking about built environment, it is modifiable by, for example, urban design. What we see is in the high stress environment, there's suppressed self-proliferation, which means to suppress neurogenesis. And you have increased neurogenesis in the high reward environment. This is in an animal model, and it has been replicated in humans. It's just, there's more data from the animal models thus far. Here what we have is, this doesn't matter, it's different parts of the brain, but the take-home story is, if you were first exposed to a high stress environment, and then there was subsequent exposure to no stress environment, you have worse cognition. Even though you go back to kind of a safe, okay environment, your cognition, which is one readout of, affect, it's not affect, but it can be part of the cluster of symptoms underlying depression, for example. You have worse cognition. Subsequent exposure to high stress environment. Now, if you're stressed for a second time, this kind of cumulative risk theory, this multiple hit kind of hypothesis that exists, where if you have multiple traumas, it can have this dose response impact on your well-being. You have more anxiety. Here, the initial exposure in early life of the animal to high reward environment, the outcome is protective. How? Because in no stress environment, you have better cognition just from that enriched environment. And in high stress environment, you have less anxiety as compared to animals that had either no reward or those that had obviously worse conditions to start with. So here is just a summary of the two mechanisms that we talked about: epigenetics, so changing gene expression without changing the genes, and neurogenesis, the integration of adult-born neurons. And so what do they do, just to tie it back to the slide? Essentially, the really simple way of thinking about it is that they modify pathways related to reactivity, adaptation, and growth in ways that either benefit and increase resilience or that hinder it. So last two slides. What are the roles of families and communities in this? Well, we have, in just a few slides, I've shown you that there is a mechanism by which us as biological beings can read the environment, right? And we're beginning to understand that. These epigenetic changes, these changes in circuitry, these changes in receptor expression, gene expression through epigenetics, et cetera. Well, if environment can impact us, and we've seen risk factors where an adverse environment can impact us adversely, the opposite can be true too. That enriched environment and cities and structures that are built to foster and are conducive to help can enhance resilience. And so what are some examples of that? So families and communities, kind of a smaller scale, we have the enriched microenvironment, right? Are you reading to your child at night? Is there time for play? Is there time for engagement with the parents, with the siblings? Is there secure bonding, parental care, connection, and parental mental health, and especially maternal mental health, which is a big one. And it's sometimes hard to parse because there's a biological component to that, but there's also elements of, mom with peripartum depression is much less likely to engage in kind of fostering behaviors. And we've seen this in animal models, and we've seen this countless times in humans, Thank you. Opportunities for community engagement, so now at the community level. Social cohesion, equity, justice versus the experience of discrimination. These aren't just things that I've randomly thrown together. I mean, behind each of these, I'm happy to do it. I could send you 30 papers that show this in various different models and in humans, and in both directions, how they can serve as risk factors, but how they can also serve as protective factors. Finally, role of the built environment. How can we use space to enhance resilience? So some ideas are developing this enriched macro environment by creating a secure, safe, and clean environment. So let me make that a lot more specific. So one really easy concept is clean environment. If you're living in a house that's moldy, has not been taken care of, it's in the housing projects, you have lead in your water, for example, well, let's start with lead. Lead has important impacts on neurodevelopment. Lead exposure, mercury exposure, arsenic exposure that might be in well water, which may not be an issue here in New York, but in parts of the world where I work, it's really important to think about arsenic in the ground and mercury in the well water. Well, that impacts the developmental trajectory of the brain. And so, a kid who's been exposed to adverse childhood experiences and lead, their outcomes are likely to be impacted. Security, right? Security, the ability to feel safe and not be exposed to violence, that's a clear way in which the mechanism between that and how resilience can be impacted and mental health can be impacted is clear. In built environments that promote healthy behaviors. So one other thing that increases neurogenesis in the brain is exercise. And so communities where there's green spaces and there's design for people to go out, where they feel safe enough to go out, that's an important element. And then opportunities for enjoyment and reward. As I mentioned to you, we focused on the fear circuitry, but it really is that. It's mental health, not mental illness, right? And the health is not just the absence of illness. It's the ability to thrive and have a sense of well-being and to engage in your community in a meaningful way and give back, etc. And so environments that can do that serve as this enriched environment promoting resilient behavior. And then access to resources. And I did put the versus scarcity in there as a shout out to someone who has left, I think. Oh, no, maybe, I'm not sure. But we were talking about scarcity and this idea of access to resources, financial resources, employment, all of which can have important mental health impacts, not very clearly logistically. So can you pay for health insurance? Do you live in a clean enough environment? Can you afford to pay for medical coverage? Are you going to adhere to your treatment because you can actually go and go get it physically? And then access to services, health, housing, and education. So these all, through the intermediary of mental health, can impact resilience of all of us. Thank you.